Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone, and welcome to the second installment in the QC Flick pre-hackathon webinar series. The Future Leaders in Quantum Hackathon, or QC Flick, is an event co-hosted by the International Telecommunications Union in collaboration with the Quantum Coalition, a group of students in quantum computing, like myself, from around the world. This hackathon is focused on a vision of the role emerging technologies will play in building a smarter and more sustainable future. To sign up for the hackathon and get notified about the remaining pre-hackathon events, check for updates on the AI for Good website or at quantumcoalition.io. Today's workshop is a beginner's guide to exploring quantum for social good. We are lucky to have with us Simon Kramer, a quantum applications consultant at the Netherlands Organization for Applied Scientific Research, which specializes in applied research centered on global welfare, health, sustainability, and safety. Simon's core focus area is on use case development for quantum computing and quantum sensing. Today, Simon will get us excited about the future of quantum information technology by giving us a valuable cross-sector perspective on the real-world applications of quantum computing. Simon, thank you so much for being here, and the floor is yours.
Thanks, Ben. And let me quickly share my screen with you guys. So. Yes, like Ben mentioned, I'm here to tell you a little bit about how you can use quantum technologies for the social good. Quickly about myself, I'm what we call a quantum application consultant. I have a background in mathematics and computer science, and I work at TNO, the Dutch research organization, also in close collaboration with Quantum Delta NL, the Dutch sort of quantum ecosystem building organization. And today, I'm sort of want to give you a bit of an eclectic mix of different projects we've done, different examples of quantum technologies within the, call it the positive benefits you could get from those technologies. And I'm just going to give you a broad range of topics. First of all, I want to show you the applications of quantum technologies in the energy transition, and more specifically, a visual that we made in there. And I think it's quite a nice showcasing tool that we made for exactly that purpose, to showcase different use cases along different domains of the energy transition, and through this make those use cases more accessible for end users, namely the end users that actually work in the energy transition. And to do this, we basically just scoped the energy transition using the Dutch energy system plan, and then looked at tons of literature and had interviews with experts on how to do this, where we then ended up with a visual like this. Which we hope makes the whole topic of the energy transition with quantum technologies a bit more accessible. Just to give you a bit of a graphic feeling about those topics, and basically saying like how many different themes there are that could be affected by quantum technology. So if you zoom in, for example, here in the energy grid sector of the visual, you can see tons of use cases like real-time cable monitoring, forecasting energy usage, battery monitoring, and we try to make it as accessible as possible with all these little icons and visualizations. Or you could go to the side where we have the wind sector, where you then see things like wind direction alignment for wind turbines, which could be improved by optimizing methods through quantum computing, but also through quantum sensors that could be placed on windmills to detect minute changes in wind directions. Yeah, and basically such a visual, we hope, would make it more accessible for end users within the energy transition to actually engage with these innovative technologies to make the step to look into those things a bit easier. And here you can see we also made this visual into an interactive version, which you can access through the internet. And then you also get tons of extra information per use case. And we're making more visuals in the future. So maybe this is just already, if you want to get going with quantum technologies, having a look at such a visual, like a very accessible overview, might be cool for you. So then let's see, getting back to what we wanted to do, quantum application development, I'm going to give you some examples, specifically some examples about computing use cases and sensing use cases. But let's start with computing. So quantum computing, I'm not going to get into the details of the technology because I'm assuming you're already somewhat familiar. Either way, we would blow the scope of this webinar if we're doing this now. But quantum computing is generally just a hardware that theoretically can be really good at certain calculations. Not all calculations, but some calculations can be really good. It's a different information system than the bits that you're used to. So you need to think about how you encode your problems into these computing hardware. But where are we at this moment? Well, we're in the so-called NISQ era, which means noisy intermediate scale quantum, which means we do have working quantum computers. That is very nice. It's not just theory. We could actually build them. However, we don't have anything in terms of a quantum advantage on actually useful problems with those computers. They're simply not good enough yet. That's okay. We're expecting that this is going to happen within the next years, but it's also not a given. So we might be close, though, to achieving quantum advantage already in this sort of short term by saying, hey, if we now take the limitations that we have on quantum computing hardware at the moment and try to focus what we can do with those to very specific use cases. So basically build and develop very specific hardware for those use cases and build very specific software, and we might be able to get quantum advantage in the next couple of years before having like the fault-tolerant quantum computer that has millions of qubits. Generally, if you look for use cases for quantum computing, it seems a bit like you could find them basically everywhere. Optimization is often used as the standard example of a use case for quantum computing, and you could find optimization anywhere basically. But we would ask to be like a little bit more critical what are actually use cases that could really benefit from quantum computing and not just using it for the sake of using it. So now let me give you a few examples. The first one I want to mention is quantum application development we've done together with Alliander. Alliander is a Dutch network organization. They basically maintain a large part of the electricity grid. And we looked with them together at something which is called the N-1 problem. It's a problem that comes up when you do grid resilience calculations. So basically you could imagine here on the right, you see an energy grid. The orange lines are cables and the white circles are just substations or end users, etc. And now you want to imagine that this is a network connecting all those substations. And if one of those cables fails, Alliander needs to make sure that they can still connect all the substations and end users with the remaining grid. So that basically means from N connections, I go to N-1 connections. Am I still able to run my electricity grid? And for Alliander, that's the problem that they can solve at this moment. But with the energy transition, you get more electric vehicles, more batteries, more solar panels, a lot more, like your energy grid is just going to get a lot more complex. And what they need to do in the next years is every time a new customer connects to the grid, they need to be able to check if this resilience that I'm explaining here, this N-1 problem, is still satisfied in the grid. And that's going to take up more and more computation time. And this is why Alliander is now looking into potential solutions, how they could do this in the future. So what are Alliander's ambitions in this whole project that we did with them together? They wanted to learn about quantum. That was the main goal. They wanted to inspire employees and stakeholders with the innovative technologies that they're looking at for future developments in the energy transition. And they wanted to contribute to quantum research. And they really wanted to have an active presence in the quantum community. What you don't see here, what their ambition was, is solve that problem right now. because this is not what quantum computing can do for you. They can't solve it right now. However, how did we deal with this problem? It was a very collaborative approach, which is something you would always have to do when you develop quantum applications for end users and for actual use cases, where you work closely together with them and make sure that the problem that you're solving, like the algorithms that you're developing, actually still solve the problem. And as the result, Aliando got a lot of, or we got a lot of understanding of the n-1 problem and understood the computational complexity a lot better. And we implemented the problem on 3 different types of quantum hardware, where we learned about the advantages and the disadvantages of those hardware platforms. And we, in the end, open sourced our results and all the code we developed. And there was a lot of dissemination that we could do at different fairs, etc. And again, like you see, we didn't solve the problem. But I don't think that's an issue, because we started then a longer-term collaboration with Aliando, where we kept going and looked at other use cases that they have, where quantum technologies might be of use. So the next one, it was sort of a similar kind of problem in the sense that it's related to grid modeling and figuring out how your grid would react to different scenarios. What I found really interesting in this one, though, is that we actually ended up finding classical methods that Aliando can implement now to improve the calculations that they are doing at this moment. And why did this happen? Well, because we took a really deep look into the problem that they have with, let's say, our quantum heads on, which then ended up in new ways that we thought of and how we could tackle such a problem.
Simon?
Yeah.
Actually, could I ask you a quick question before
Please.
moving on from the n-1 problem? I think
Go
it'd be
for it.
beneficial for the hackathon participants. So, like, what are some indicators that a problem might not actually benefit from looking into a quantum algorithm to solve it? Like, what makes the n-1 problem a good candidate for, oh, this might have an algorithmic speed up from quantum computing?
In that sense, the n-1 problem was a good problem because the optimizational challenge would grow and grow over time, because the energy grid would grow. And you could really say that, like, the classical solutions that were there at this moment would not be able to solve those challenges anymore. So on the one hand, that made it just a very important problem to solve, which I think is very motivating in that sense. And then quantum computers tend to also be quite good at these sort of graph problems. If you have a problem that you can encode in a graph, chances are that you could somehow relate that to quantum computing algorithms that are already existing. Yeah.
Oh, wonderful. Okay, so the size of the problem grows really quickly, and this is the kind of problem that a quantum algorithm might be able to tackle where a classical algorithm can't.
Exactly. Yeah. Okay. After doing this, actually, after we had the second project with Aliando, we actually also expanded and did some quantum sensing work, which we're doing still at this moment. But I don't want to get too much into detail into this now, because quantum sensing we're still going to do in a little bit. So why is this now important that Aliando did application development, even though the hardware, the quantum computing hardware, is not there yet? Well, they do build understanding of those innovative technologies, and they build it based on their own use cases. They don't just understand it from, hey, quantum computers are good at optimization. They understood how it relates to the n-1 problem. So that enables them in the future to identify opportunities as soon as possible. And like we've seen, considering a problem from a quantum viewpoint can, and actually in this case also did, lead to classical improvements. So we understood the problem on a different level so that they could then implement classical improvements in their systems. And this is specifically for me one of the most important points. Aliando shares domain knowledge that is really crucial to develop quantum solutions. Otherwise, researchers that will build the technology, that will build the algorithms, they don't really know which issues they're actually solving. And therefore, they might even not solve the useful things. So being engaged as an end user there that owns the problem is super important for the whole development of quantum technologies and quantum algorithms. A second example that I could quickly show is quantum machine learning for satellite imaging. I thought this was a very fun project that we've done where wait, where's my slide there? We wanted to see if quantum computing can actually help in analyzing those satellite images. Basically, a satellite took images from coasts, and we wanted to figure out if we can estimate the water depth from these multispectral images that such a satellite took. And this is important for various use cases because you want to, with your ship, you want to make sure that the water is always deep enough that you wouldn't crash onto something. And if you know these, like the water depth from all over the world, and you can easily map them with those satellites and monitor them, it could help you in optimize shipping routes, for example. And so what we did there, we actually looked at a quantum variational classifier, which is sort of a machine learning equivalent, a quantum equivalent of machine learning. And it's quite an interesting one because this is one of those algorithms that could potentially work already in the near term and have advantage over classical computing there. Because it's sort of a mix that you do between quantum computing and classical computing, where you only do certain calculations on the quantum device and then go back and forth very quickly between the classical and the quantum computer. I could go more into detail here, but we did make a video about it, which I think explains these things a lot nicer. So I would encourage you to have a look at this, where we also explain a few more basic examples and like basic properties of quantum computing. So how the qubits behave, how quantum circuits look like, and also how quantum machine learning works. So yeah. Then I think I would, for now, go to quantum sensing exampents to give you a bit
Could
of
I ask a
Yes,
quick
please.
question before you head on?
Go, Ben.
Yeah, sure. So you mentioned that this quantum variational classifier is an algorithm that has near-term applications, especially because of the way that it works along with classical hardware. So I wanted to ask, is the size of the input data actually feasible to execute on today's quantum hardware in a way that can, produce solutions that may be more accurate than a classical computer? Or like, how do you verify whether there's sort of an advantage to using a quantum computer in the near term?
Yeah. Your second point, quantifying the advantage of a quantum computer, very difficult for all those sort of machine learning problems. Because every time you would deploy any machine learning algorithm on your data set, I think it's quite difficult to say, okay, did that now perform well on this data set for reasons that I don't understand, but my precision and my accuracy is higher at the end. But is the overall quantum machine learning then better than classical machine learning? That's hard to say, I find. However, in this case, what your first point that you mentioned about the data that you need to encode on a quantum computer, I found personally this use case super interesting because basically the number that people always mention for the quality of a quantum computer is the amounts of qubits. And this is usually the limiting factor in encoding data. But for most quantum machine learning algorithms, and especially for this quantum variational classifier, you actually only needed 1 qubit per feature that we wanted to put on. And that is then, this is the cool thing about quantum information there, that you can encode a floating point value, which we wanted to do here, which is the brightness of a certain pixel. You can encode that on 1 qubit because your qubit has constant states basically between the 0 and the 1. But yeah, I don't want to get too much into detail here now, but I do find it a very cool project. So maybe you could check out the video then to learn more about it.
All right, thank you.
No worries. So then let me go to quantum sensing and some examples for it. But first of all, how should we think about quantum sensors? What are they? A typical sensor, any sensor that you know that you have in your phone, basically also your eyes and your nose, there are sensors. The only thing that they do is they take a stimuli that comes from the environment and somehow translate that stimuli into an electric signal. And then it goes into an electric system, which can be your eyes translating a photon into an electric impulse to your brain, or your phone that notices that it's rotated a little bit and then tells the phone, hey, switch the image to landscape. A quantum sensor is the exact same thing. The only thing is now that the sensor would use a quantum system to mediate that information transfer from stimuli to electronic system. Generally, quantum sensors come in many shapes and forms. So you can have super big ones, super small ones, extremely expensive ones, very cheap ones, all of this. And some of them are actually already the gold standard in certain measuring use cases, like right now. And some quantum sensors are still very much in early research. You can't really say that quantum sensors have a general benefit over classical sensors. It often comes down to the sensitivity of the quantum system that you use in there, but that doesn't necessarily mean that the overall sensor has higher sensitivity. So it's very, very use case specific. And I hope that I can also show you that in the next couple of examples. First of all, here you can see some actual quantum sensors that you can buy right now, that are in use right now. Here on the bottom left, for example, you see a gravimeter, which is here deployed on the Mount Etna. It's an absolute gravimeter, and in comparison to classical gravimeters, it actually has advantages in price. It's significantly cheaper. It uses less energy, so it's a lot easier to deploy on these kind of places, and it has an extremely high sensitivity. So if you would take this little cylinder that is there, well, it's not that little, but if you would that cylinder, put it and move it up by a centimeter, it could tell you, hey, the gravitational field changed. I got to be higher now. You also see on the right, for example, this is an interferometer where you basically shoot photons along those long pipes into both directions. So this is a significantly bigger quantum sensor than you can see on the left side. And we're also going to get into some more details about the other images. So I don't want to get to it now. There's a lot of different available quantum sensors. And in this table, we kind of collected most of them that we could think of. And as you can already see, there's tons of different quantum systems that could be used as the quantum system that mediates the information transfer that I already mentioned before. And basically, you can see here on the vertical axis, you can see physical quantities, which those quantum systems could be sensitive to and where it would make sense to build a sensor for. The different colors in this actually mean how technologically advanced the sensor systems already are, where the dark color must be, I think, a TRL 7 or above already. And I wanted to give you a few examples from those now, starting with optically pumped magnetometers. They can detect magnetic fields very well. So there's one of these here at the top left. As you can see, a very tiny device. If you want, you can build it very small. Basically, how it works is shown here in the middle, and it's quite simple if you boil it down to just this graphic, where you say there's a glass cell in there with atomic vapor. You shoot a laser on this. All the atoms basically align with this laser, and you can detect on the other end how much light goes through. They're basically transparent in this state. But if you then apply a magnetic field, you detect with your photodetector on the other end that there's not that much light going through anymore. And you can basically correlate the amount of light that you get to the magnetic field that is around. And those sensors are extremely sensitive. And so much so that this product that you see at the bottom left is basically the gold standard to measure magnetic anomalies in open waters. So you would take this big device, which has a tiny OPM hidden in there, and you would drag it behind your ship and then measure magnetic anomalies in open waters. One use case I want to show you, which I think is very nice for OPMs, are brain scans. So here on this map, you can see the availability of brain scans in different parts of the world. And as you can see, yeah, in the United States and in Canada and in West Europe, you can get tons of them. In other parts of the world, that is not that easy to get a brain scan. And now what we hope we can do with OPMs is make them more accessible and cheaper and spread them through this more all over the world. But also, you can see here on the right, you have this pink helmet that the lady is wearing there. this would be a 3D printed helmet where you can put tons of those little OPMs in, which would then allow you to measure magnetic field, like the scan your brain while actually moving around, and measuring, like correlating these movements then also to the brain activity. And also a massive advantage. You can match those helmets then to any person that needs the brain scan, because those things here on the left, the big squid brain scanner devices, they only work for a certain head size. They, for example, don't work for kids. There are none. So I think this is a very nice example of a positive use case for quantum technologies in that sense. I would go to a next example, squids, which is superconducting circuit, which is also something that is used for quantum computing a lot. And here I want to show you something where they also can be used to measure magnetic fields. And just very briefly show you this company. It's called Chipiron. And they built MRI scans based on those squids. And then again, the advantage now is not like, oh, our scans are a lot more accurate than normal scans. No, the idea is these scans are a lot cheaper and a lot easier to use. You can work, like I mentioned here from the bottom, it works from a standard outlet. You don't need to be a technician to operate it. You don't need a shielded room, because these are like the main issues that we have in different parts of the world, and that it's not always that easy to get a magnetically shielded room that is vibration damped from the ground up, and then to buy a millions of euros MRI machine. So this would also again be an example of quantum technologies that would just make this technology more accessible all over the world. And I wanted to highlight this because often quantum technology is seen as like the expensive, innovative technology that is only affordable for the rich countries. But here specifically, it's also about making things cheaper than they are at the moment. Did you have a question, Ben?
Oh, yeah. Could you mention briefly what SQUID stands for?
Yeah. You have it in, do we have it in here? No, the superconducting quantum interference devices. Should have put it in the title. All right, and now the last example I would have for quantum sensing, NV magnetometers. So this is nitrogen vacancy. NV stands for nitrogen vacancy in this sense. And these are diamonds with a quantum defect. So that means there you basically synthetically grow a diamond, and you infuse nitrogen atoms into your diamond lattice. And then you basically have nitrogen atoms and vacancy, basically where there's then no atom in this lattice. They find each other, and in between you have a free electron that is then sensitive to magnetic fields and temperature, for example. And with some smart operations of this diamond, let's say, you can shoot a laser at it, you can manipulate it with microwaves, and then with, again, a photo detector at the other side, you can figure out how much this diamond glows, let's say. So you shoot a green laser and it glows red, this defect. And basically in correlating you can correlate the microwave frequencies that you apply and the luminescence you measure from the diamond to then figure out how much magnetic field how strong the magnetic field around it is, or correlated to the temperature. Below here, you can see some devices that build exactly this. So there's lasers and microwaves and the photo detector. And here you can also see the green glow of that laser. Yeah, and with these devices, you can, like I mentioned, do very high sensitivity measurements of magnetic fields. And I wanted to show you one example for this because I also think that this is quite a special example in the sense of what are the benefits of quantum sensors. These diamonds are very robust. So you could deploy them also in extremely harsh conditions. For example, in batteries. Because in batteries, there's a very toxic environment with all the chemicals that are in there. But we would maybe still want to measure inside a battery how the current is flowing through there, or the temperature of the battery inside. And now with we're trying to do this by fitting such a sensor based on this diamond inside a battery. So then you would leave the laser, the detector, and the microwaves, etc. You would leave all the like complicated control electronics in that sense outside of the battery and only put the diamond in there. And by doing this, could get measurements that we haven't seen before. Those measurements about currents and temperatures inside a battery, which could help us design, on the one hand, more efficient batteries, maybe, because we understand batteries better. But it could also be something that you could use in operations, where you say, while the battery is charging, you can monitor its state, it's the current that is flowing, the temperature, so that you could maybe say, hey, a little bit less current while charging right now to extend the lifetime of the battery in the end. So it's also a use case that I think can be very, very relevant for the energy transition. All right. Yeah?
Yeah, could I just have you the quick questions?
Please,
All right.
yes.
Yeah, so you mentioned back when you had the grid of different types of quantum sensors and some of the boxes were colored dark blue and light blue, you mentioned like a tier classification. I wanted to ask you how do sort of people evaluate the maturity of these different types of technologies, or do you have any more specifics about how these are classified?
Yeah, it's basically the TRL levels is like I think worldwide recognized system of figuring out how far a technology is. And it's really about, if you have TRL1, then someone thought of, hey, like those defects that we find in a diamond, I think they're sensitive to magnetic fields. Could probably do a sensor with it. Then you're at TRL1. And then you kind of like build up to the next stages by saying, someone made a first demonstration in a lab where they could see that the fluorescence changes of this diamond. Then you get up in the TRLs. And at the end of the spectrum, you end up with products that are so well built and like can be sold off the shelf. So there are very concrete sort of guidelines on how you're judged in your TRL level, in your TRL. But I can quote them all for you now, yeah.
Okay, thanks for adding that context. Yeah, that's really helpful. And then maybe you could elaborate a little bit more on what makes NV magnetometers actually good to operate in harsh environments in comparison with other things. It might not be obvious why, a squid device, is not suited to operate in a harsh environment.
Yeah. It's really the robustness from those NV magnetometers comes from the thing that senses what you want to sense is this defect, and this defect is enclosed in the diamond. And the diamond structure is just generally a very, very robust structure, one of the most robust structures we know. And so if you compare that to any other sensor, for example, like a squid is now a very strong counterexample, because a squid also needs cryogenics around it, and it's a huge device. And in that sense, a lot of sensors would always need like close to the thing that measures something, need control electronics, need a PCB or something, and all those kind of stuff would break if you have it in the battery. And now the cool thing with the NV magnetometers is the diamond is very robust, it's not going to break. And the only way you need to interact with this diamond is shoot a laser onto it and collect the fluorescence and figure out how you can get some microwaves onto it. But then basically you can leave your laser and your photo detector all outside of the battery and only put the very robust diamond in there, and you try to connect it with a glass fiber. And this one you could then shield from the harsh environment in the battery. Yeah.
Brilliant. Thanks for that answer.
No worries. Okay, then for the final section of my talk today, quantum application development specifically for social good. What are the opportunities and the challenges? And maybe what kind of tips would I have? Or, well, tips is maybe a strong word, maybe what I would hope for how quantum application development can work there. So to the opportunities and challenges. You will have the technology push and the application pull, always in any technology development. Which basically just means there's researchers in the lab building a quantum computer, not knowing what we're going to use it for. And there's people like Aliander that say, I have a computational problem. But the people in the lab, they would also really like to know, what should that thing that we're building, what should that be used for? Do we need to tweak it in certain ways so that it really fits that application? So by now saying we focus on applications for the social good, we can maybe also steer already a little bit the technology development to fit the use cases that we care about a bit better. By also now saying, hey, we consider quantum technologies that will come up into the future, we can work on societal readiness before technological readiness. We kind of missed that step a little bit with AI, right? It just suddenly was there and everybody used it and no one really knew how to use it. And for quantum tech, we're hoping to avoid this. A bit of a challenge, but maybe also an opportunity for quantum application development for the social good is the dual use of technologies. Like all the technologies that we discussed here, and even though we developed them maybe for a very specific use case, they most likely can also be used for a different use case. And maybe that is then a use case that for yourself does not count as a use case for social good. That's something that people working in this field, but I think everybody working in any technology development should be aware of and should check in with themselves how they feel about this. Which then also gives another challenge. If this is the case, who should actually fund all that technology development? Should we say that it's mainly, I don't know, call it UN agencies, for example, and public institutions that should fund the development of quantum computers because they want to use it for good? Or should we say, hey, maybe if other parties are also interested into this, why should we not let them develop the technology and we use it at the end when it's there? It's a lot of, like, these are all open questions that I have. I can't really give answers there. Yeah, the hype of quantum, an opportunity and a challenge in its own, because obviously it helps that there's so much hype about it, that there's a lot of funding about it and a lot of enthusiasm. People want to work on it. People are excited. But at the same time, we have to make sure that we don't overpromise what quantum can do. And this is really something I would also try to appeal to everybody in the hackathon. Don't try to feed the hype with wrong assumptions about what could be done with quantum, or wrong promises. A challenge is, how do you motivate end users about future technologies? Like, how can you make sure that someone that is interested in a specific use case of the social good, how can we make sure that they are actually also motivated to work with the technology development if they might not be able to use the technology right away? And the biggest competition will always be classical technology. So you really have to find a very specific use case to find that advantage for quantum technologies over the classical one, because we just have very good classical technology. And a bit of a challenge is for all of quantum technology is always accessibility. So how can we make sure that if we have a quantum computer that is extremely good and that solves a lot of challenges, how can we make sure that everybody has access to those quantum computers? And then finally, maybe some suggestions for application development that I think are really important to consider. Be very clear with what you want to achieve. This is also going back a bit to the Aliander project that I showed you. Do you want to learn about quantum computing, quantum sensing? Do you want to learn how it would fit to that use case? Do you want to learn about how the future for this use case might look like? Or do you want to solve it now? If you want a solution now, then especially for quantum computing, it might be reasonable to look at other technologies actually. And it's not a bad thing. It's just something that you should be very clear about what you want to achieve when looking at use cases. Really understand the problem. So don't try to assume what the issues of a certain problem are, what a certain sector needs. Really try to involve domain experts from the start. So don't come up with an optimization problem that you want to solve that you think is important in the energy transition. Really involve the experts from the energy transition. and be very specific in your use case definition. So really narrow it down to make it concrete so that you can actually show there is use for quantum in that specific scenario. That is also, for example, like I mentioned with the NV magnetometers, it makes sense to put a diamond into the battery, but if you want to measure outside of the battery, then maybe the NV sensor based magnetometer would not make sense anymore. So really be specific in your use case definition. Yeah, and then this is also a bit related to the hype. Just be honest with the outcomes of it and don't be afraid to fail in that sense, because I have the feeling quite often there are use case studies about how quantum could fit onto those, and in the end it's always like that, oh yeah, it could fit in the future and sure, might work. But I think people can also be a lot more honest there and just say, hey, we don't need quantum here. Like, it's great how it works at the moment. And I would say this is also a great result, and don't be afraid to say that. Yeah, I put a few resources at the end of my slide here that might be interesting to look at. For example, the Open Quantum Institute, which is an institute in CERN, which collects quantum use cases and helps those projects actually as well, the project teams, to work on quantum use cases that are related to the SDGs. The Center for Quantum and Society in the Netherlands is a center that is specifically for the societal impacts of quantum technologies, but also trying to find the quantum for good use cases. And I briefly wanted to mention the toolbox that we developed at TNO, where we collect open source software that might be useful to you guys, or just a nice way to interact as well. Yeah, thank you very much for your attention.
Thank you, Simon, for that wonderful presentation. I have prepared a few questions that I think might be interested to the audience if you have a few more minutes.
Yes.
So first, in the beginning, you mentioned that literature review, and you created a great graphic to sort of communicate all the different areas where quantum computing can have a near-term impact on technologies in the future. I think like some hackathon participants who are doing the education track might be interested in writing a similar literature review. Obviously, the challenges aren't out yet, but could you talk about the process of writing such a literature review, and especially like how do you bridge the technical gap? I'm a researcher myself. I feel like, you know, getting through one paper entirely is really difficult. They're all very complicated. How do you like get such a broad overview?
Yeah, it's a good question, because we also found it quite difficult, yes. For the energy transition specifically, there were already quite a few papers out there actually where people considered use cases for like use cases for quantum technologies that could be relevant for the energy transition. So in that sense, doing like your typical scan of literature that you find online was already super helpful. What we think what was very helpful then as the next step was trying to make sense of those use cases, at least on a high level, that you understand what problem they're aiming towards, and then you can go and check it with really the domain experts. So we talked to a lot of people within the energy transition to say, hey, look, we found, and we don't know anything about the energy transition, but we found that someone suggested it would be useful to align your wind turbines better with the wind, and they have the suggestion for a sensor. Is that a problem for you to align those wind turbines? And specifically those interviews and those chats, they really helped us. Yeah.
Okay, that's great. So it takes some of the burden of communication off of you, like, you know, to sort of be able to talk with domain experts and gain from their knowledge, rather than having to become a, you know, 100% domain expert yourself in order to understand the problems.
Because you just won't be able to. And so I think your focus should always be on trying to communicate to those domain experts what the benefits of the quantum technology in that specific use case could be. And you will get this from the paper that you found. And then make sure that you kind of like take the the hype words that might be used in the paper a little bit away, so that the domain experts can really judge for themselves, hey, this is a problem that is relevant, and if a solution like this could work out, it would be useful.
I see. Do you have any further tips for people who are looking to communicate with experts in other domains? So, for instance, scientists who know a lot about quantum computing, how do they communicate to someone who's not knowledgeable in quantum computing about
Mhm.
a problem that you might be able to solve with a quantum computer?
Yeah, yeah. I think the general tip is take longer than you think to set the stage of it all. Um, because I think I ended up quite often already explaining qubits and how they point up and down and to different sides. And only after a while, I realized that we didn't set the stage well enough. So we weren't even aligned on what a computational problem is. That wasn't really clear. So I think really starting more from the beginning than you think always helps because the person you're talking to will speed you up if they know about it.
Mhm.
Um, and then I think finding analogies for technologies that they already know is also very useful. So I ended up quite often comparing quantum computers to just GPUs to say, hey, it's not a thing on its own. You will always need other things around it, like classical computers, etc. And certain calculations you can push to it. And then people realize, oh yeah, I know what a GPU does. And if this analogy works for them, great. Yeah, and probably it also makes sense if you want to talk to the really the domain experts from different fields, leave the qubits out for a bit and just focus on what the results could be from a calculation that you do on a quantum computer. Yeah.
Okay, that's wonderful. So you mentioned a little bit in the engagement with Aleander that they were more focused, maybe not on finding an immediate
Mm-hmm.
application where sort of a they see like a direct benefit from using a quantum algorithm over a classical one, but instead they were focused on quantum readiness. This is something I found a lot in the quantum computing industry that people aren't sure exactly how long it will take to
Mm-hmm.
get this technology to a place where it starts to deliver those concrete benefits. And some people also talk about, the possibility of a quantum winter, whereas the technology develops more slowly, then industries lose interest. So how would you hope to see industries continue engaging with quantum computing,
Mm-hmm.
and the role that end users play in all this while the critical engineering challenges are being solved?
Mm-hmm. Mm-hmm. Yeah, it is a very complicated world in that sense. To do application development already now, when we're not sure where the technology is headed to, and I think the interesting thing that you can always do about it is to say, hey, if we look at a problem from a different viewpoint, you will learn about your problem. You will learn about quantum as like a side thing. This is the angle that we chose now, but you will really learn about your problem. And I think this is one of the biggest benefits we have at this moment. And then also, like I mentioned, I think we are in a stage now that there might be the quantum advantage also on NISQ hardware that we could find if we're really ambitious about the use cases that we look at and how specific we make them. Um, yeah, it's more this with Aliander when they thought about quantum computing for their problems. They were super curious to find also quantum advantage, of course, but they at least didn't choose problems that they need to solve today. And I think this is the right approach to say, hey, we want to solve something that is going to be very important, and we want to figure out if this could be an option for it. Yeah. A little bit different for quantum sensing though, because there obviously you could find the quantum sensor that really solves your issue today. So there, the approach can be a little bit different.
Okay, wonderful. Yeah, that's great advice. So now we also have some questions coming in from the audience.
Mm-hmm.
So, well, this is less a question, but later, would you be able to post a link to the visual about the energy transition, or is that
Yes,
available somewhere?
yes, I can do that. I can do that.
Okay, amazing. And then another one of our audience members asks, is it possible to receive the presentation in our email? This would maybe be a question more for the
Mhm.
infrastructure people. I'm not sure about that.
Yeah.
Okay, wonderful. Well, okay.
Just to quickly just jump in there,
Mhm.
we certainly could. If you could send us your presentation, Simon, then we can add it to both the webinar page and the neural network as well.
Mm-hmm. Yep.
That's awesome. Okay, one last question, I think, from me. So, when you're talking about using technology for social good, like for instance in the brain scans, obviously this might, in some instances, throw up a lot of ethical questions. If one of our hackathon projects ends up raising an open ethical question, how would you advise a team to approach this?
Good question. In the Netherlands here at Quantum Delta, also with the Center for Quantum and Society, they developed actually a framework to look at the ethical questions regarding quantum technology. It's called the ECTA, I believe, so the Exploratory Quantum Technology Assessment Framework. And it's a longer framework that you can really use to see what kind of questions should you ask about ethical concerns, legal concerns, societal aspects, etc. Which is, like I mentioned before, really focused on this societal readiness before technological readiness. So that would maybe be a starting point that I could suggest, yeah. Which I can also
Okay.
share a link to later, yeah.
Oh, that would be wonderful. Thank you. Okay, I don't see any more questions coming in, so I think it's a good time to wrap up. Thank you so much again for speaking with us today, Simon. To our audience, we look forward to seeing you again on March 25th with our next pre-QC Flick workshop, the Introduction to Quantum Pedagogy. Please don't forget to check for more updates on our website, quantumcoalition.io, and pre-register for the Flick Hackathon that's taking place this May. Thank you all, and have a great day.
Thanks, bye-bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.